This virtual lab will address inductors, also known as solenoids or coils for simple. A coil is a wire that has the shape of a noodle. As we are going to discover, the shape of the wire on its own revolutionized the 20th century. A coil, shown above, is connected to a bulb and a voltage meter. We approach the coil with a magnet. As the magnet is moving towards or away from the coil, current runs through the circuit, and the bulb lights up and the voltmeter registers voltage. As we approach the magnet, we are effectively changing the magnetic flux going through the coil. Then the coil generates a current, denoted here as V sub L, across the inductor, which lights the bulb. The faster we move the magnet, the more brightly the bulb lights up, which essentially means the greater the current running through the circuit. Notice that when the magnet changes its direction, the voltage also changes its direction or sign. But how or why exactly does this happen? In the presence of a magnetic field, the coil produces a current which, in turn, produces another magnetic field, opposing this time the change that we are trying to induce with the magnet. Now, how vigorously the coil is exhibiting this opposition is expressed with a so-called inductance, here denoted with the capital L. This is known as the famous Michael Faraday's law of induction. As for the why this happens, to be honest, there is no why. This is because nature works this way. Nature is geared towards recalibrating herself in the presence of a change. Well, simply put, nature resists in the presence of change. There are many other expressions of the Faraday's law in other sciences, spanning from chemistry to economics. You can check my online lectures for more information. This virtual lab will give emphasis at the AC domain of the so-called resistor-inductor circuits, where most of its practical applications are found. The coil, or inductor, exhibits the exact opposite behavior than that of a capacitor. A cap, because it cannot charge instantaneously, exhibits a lag with respect to the circuit's voltage. This essentially means that the cap's voltage is maximized after the circuit's voltage, simply because it needs time to store the charge. We have observed this behavior in our previous lab. Now, the inductor does exactly the opposite. As the Faraday's law states, the inductor reacts in advance to the current change. Hence, it leads the circuit voltage. This means that the voltage across the coil will maximize before the circuit's voltage. Now, take a moment to closely observe an RC next to our LC circuit, so you better understand what we are describing. Both circuits are AC, alternating current. The RC on the right and the LC on the left. Both have the exact same resistor of 10 ohms, the same AC amplitude and frequency, namely 100 Hz and 10 volts peak. The cap is 100 microfarads, as in our previous virtual lab, and our inductor is 8.2 millihenry. These values, in fact, do not matter at this point. What really matters is the contrast we mentioned a minute ago, in that the voltage across the inductor, here shown in purple color, leads the circuit voltage, shown in red color. In contrast, the cap's voltage, shown here in green, lags the circuit voltage. As we computed the phase difference in the RC circuits, is in a similar fashion, we'll calculate the phase difference in the RL circuits. The main takeaway here is that both circuit elements exhibit a respective lead and lag just because of their physical characteristics, their physical properties. In other words, the cap storing charge and the inductor following the Faraday's law. Well, while the first is quite intuitive, the latter, in essence, the Faraday's law, is not so intuitive. But you can check your lab manual for more information. The same way we have defined the resistance of a capacitor, we now define the resistance of an inductor, namely the resistive inductance X sub L. Note that X sub L is proportional to the frequency and inductance. This means that in an LR circuit, the greater the inductance or frequency, the more inductively dominant the circuit is. Here's some algebraic implementation of what we just mentioned. Let us now observe some of the properties of an RL circuit. We are going to gradually increase the frequency from 20 Hz to higher frequencies. In purple, we show the circuit's voltage, and in green, the inductor's voltage. Notice that as we increase the frequency, the circuit becomes, as we call it, more inductive, in that the entire voltage drop across the circuit essentially takes place only across the inductor. Now take a moment to absorb this information. This animation should also provide you with additional important information to address question 2 in your lab report.
Now let's find out a couple of things about the current, shown here in orange color, while purple is still the voltage across the circuit and with green across the coil. For the record, we have exactly the same RL circuit as before. The first observation is that the current is decreasing as the frequency goes up. To verify this, take a look on the above waveforms and observe that the maximum values of the current shown on the right y-axis are indeed decrease. This is to be expected since the application of the Ohm's law dictates that the current is inversely proportional to the resistance. Since the resistance of the circuit increases, since again V sub L goes up, the current should decrease. The second important observation we can glean is that the current is 90 degrees apart with the voltage across the coil, shown here in green. We can tell that is 90 degrees apart since when current goes through zero, di dt is at its maximum. So is the voltage across the inductor, which essentially is the Faraday's law. This animation should also provide you with additional insight to address question 2 in your lab report.
Based on the previous findings, since the resistor and the inductor are in series, then the voltages across the resistor and the inductor should also be 90 degrees apart. Now, if you recall, this is exactly what we found out for the resistor and the capacitor in the previous lab. As you can figure out by now, and also by skimming through the lab manual, the algebraic expressions of a cap or an inductor in an AC domain are highly analogous. The phase difference, the respective resistances, and finally, the respective impedances. This is the virtual circuit pertinent to question 3 in your lab report. We strongly suggest that you pause the video so you can carefully observe the waveforms of the current, shown here in orange, and the voltages across the circuit and the inductor, shown in green and purple accordingly. From these waveforms, you will need to estimate the RMS values for these variables and think why your real measurements, as mentioned in the lab manual, exhibit this deviation from the virtual measurements shown here. We saw before that moving a magnet near a coil will induce current in this coil, lighting up the bulb that is connected in series. By extension, one can also test what will happen in the following scenario. Our original coil is now connected to an AC source, and adjacent to this coil we have a secondary coil. The current going through the first coil now creates a magnetic field, as the Biot-Savart law states. Part of the magnetic flux also crosses through the secondary coil. Now, Faraday's law states that this will induce a voltage, creating a current, which further creates a magnetic field, which will eventually oppose the incoming magnetic field lines from the primary coil. The closer the two coils, the greater this induction effect. You can, in fact, visualize this from the intensity of the bulb in the animation shown here. The induction effect can be more enhanced if we insert an iron core between the two coils. Because iron is a ferromagnetic material, a greater portion of the magnetic flux lines from the first coil will go through the secondary coil. This demonstrated property was described in early 1900s, open up a whole new way of transferring energy from one device to another device without even physical contact. This was one of Nikola Tesla's main contributions to science and technology, and essentially the major advantage of AC over DC. Let us highlight some necessary math. When current changes in coil 1, this induces a voltage in coil 2. When current changes in coil 2, this induces a voltage in coil 1. There is, in other words, what we call a mutual inductance that can be shown to be equal to the magnetic permittivity mu sub naught times the product between the turns of the two coils, N1 and N2, times their common cross-sectional area, A, divided by their common length, L. Let's take another look at the previous example where we had two coils with different number of turns, but the same area and length. We will also interject here a rectangular piece of iron between the two coils. One coil is usually connected to an AC source, and we call this the primary coil. The other coil is not connected to any power, and it's called a secondary coil. This contraption is also known as a transformer. Following the previous derivations, we will derive the most important relationship for a transformer. That is, the ratio of the voltages between the secondary and the primary coils is equal to the ratio of their respective number of turns. A transformer which has its secondary turns greater than its primary turns is called a step-up transformer, which means that the voltage in the secondary coil will be higher than the voltage in the primary coil. The opposite scenario is a step-down transformer, and in fact is what this animation is showing. A few important details that bear a great weight when it comes to transformers. In this example, we have assumed that all the magnetic flux lines generated from the primary coil are passing through the secondary coil and vice versa. We call this the coupling coefficient, denoted here with K. This coefficient is defined as a ratio between the number of magnetic flux lines going through the first and second coils. In an ideal transformer, K equals to 1. The mutual inductance and the coupling coefficient are related through this expression, where K again is the coupling coefficient and L1 and L2 are the inductances of the primary and secondary coils respectively. Let us see that in action. The primary coil is connected to an AC source of 1 volt peak. We vary in real time the turn ratio between the two coils from 2, 3, and on then to 4. Observe the peak voltage across a secondary coil changing from 2, 3, and 4 volts peak. Note that in green we show the primary coil voltage and in purple the secondary coil voltage. Also note that we are using an ideal transformer with a coupling coefficient equal to 1. This implies that all the magnetic field lines induced in the primary coil will go through the secondary coil. We also note that the two voltages are 180 degrees out of phase, something that is essentially supported by the minus sign in the Faraday's law and the mutual inductance. Now take a moment to absorb this visual information, and if needed, have the animation loop back and forth. Now we are going to add a resistor in the secondary coil, and we are going to call this the load. Because of the induced voltage across the secondary coil and the presence of the load, current is going to flow through the secondary circuit. Now we need to understand a very important physical concept based on which important expressions will be derived. For an ideal transformer, the electric power delivered in the secondary coil equals the power in the primary coil. And from the Ohm's law, we know that the electric power is current times voltage. Hence, the conservation of energy is expressed by this equation. Now, by considering the previous ratio equality, we derive for an ideal transformer the ratio between the currents of the primary and the secondary coil will be inversely proportional to their respective turns. Now, in a non-ideal transformer, of course, we expect that some power will be dissipated in the transformer, so the primary electric power is always greater than the secondary power. This is because some magnetic field lines generated in the primary coil will not pass through the secondary coil, as we discussed a minute ago. We will not be concerned with non-ideal transformers at this moment. Let's apply our virtual lab and see the previous statements in action. We have our ideal step-up transformer at a ratio at 1/4. Now we load a 10 ohm resistor in the secondary coil. We see that the max current is 1.33 amps in our primary. This is indicated in purple. From the previous computation, solving for the secondary current, we will get 0.33 amps, which is exactly what we get from our virtual scope shown here in green. Finally, using the Ohm's law, we have that the voltage drop across a 10 ohm load will be 3.33 volts, and this is exactly shown in orange. Play the animation as many times as you need in order to understand this very important point. Also notice that we are calculating all these values in terms of their maxima. However, the same computations would have been exactly valid for RMS values.